This is a video for percent yield. We're going to do a practice problem from your percent yield worksheet number 1. But just to remind you what percent yield is, it's the ratio of the actual yield to the theoretical yield. And when we read the problem, we need to make sure we understand which number is the actual yield, because that will be given to us in the problem. It's the amount of product that was produced in the experiment. So someone did the experiment and produced a certain amount. The theoretical yield, on the other hand, is an amount that we calculate. So this is actually where we would do usually a mass-to-mass stoichiometric calculation. So the theoretical yield is the maximum amount of product that could be produced by calculating using stoichiometry. So usually we don't reach the theoretical yield because, given various errors in the experiment, it's not really possible for us to produce 100% of the possible product. So to calculate the percent yield, we'll put the actual yield on top, which was from the experiment, and then we divide it by the maximum possible that we could produce based on calculations, which is the theoretical yield. So to do these types of problems, we will need to do a mass-to-mass calculation, and like any stoichiometry problem ever, we do need a balanced chemical equation. So I have just written the equation. The problem requires you to determine this balanced chemical equation. I skipped over it just because you should know how to do this already. There are videos to determine balanced chemical equations, so watch those if you're unsure. But this is the equation we get for number 1. And we don't need to use phases. We're more interested in the relationships, the coefficients that we needed to balance these here. But we do need to read through the problem and identify the mass of the limiting reactant and the mass of the actual yield. So as we read through this, it says, when excess potassium chromate is added to a solution containing 0.500 grams silver nitrate, solid silver chromate forms. At the reaction's completion, 0.455 grams of silver chromate was obtained. So there are two numbers in here, 0.500 grams of silver nitrate and 0.455 grams of silver chromate. So from those numbers, we have some important information. The first, and actually this is important as well. So this tells us that we have excess potassium chromate. So in our equation, this one, potassium chromate, K2CrO4, this is an excess. So we have enough of this to last for the experiment. We will never run out of it. On the other hand, the silver nitrate, we have a limited amount. We have 0.500 grams of silver nitrate. So the amount of silver nitrate we have is going to limit our reaction. So when it asks for the mass of the limiting reactant, it's this 0.500 grams of silver nitrate. That's what's going to stop our reaction. We're going to run out of silver nitrate. This could just go on. We have an excess amount of that. So the 0.500 grams is the limiting reactant, and then the mass of the actual yield, if we read on, says at the reaction's completion, 0.455 grams of silver chromate was obtained. So this is a product, silver chromate, this one, and we generated 0.455 grams of that. So the actual yield is 0.455 grams. All right, so those two numbers are very important, and we will use both of them in our calculation in part C. So part C says to calculate the theoretical yield and the percent yield of silver chromate, this thing. Okay, so first thing we need to do is calculate the theoretical yield, and we will do that by looking at the amount of the limiting reactant we have, and based off of this number, how much silver chromate could we produce if 100% of this was converted to silver chromate. So to do this, we will need to do our stoichiometric calculation, and this is going to be mass of silver nitrate, and we want to convert it to mass of silver chromate, because that's what we have. The mass of the actual yield is silver chromate. So we want to compare the theoretical yield of this to the actual yield of this. So this is a mass-to-mass problem. So we're going to start out with this number here. and we need to do some dimensional analysis. So referring to this, remember, as we're doing a mass-to-mass problem, we're going to follow all these steps. So we're going from here to here. We first need to convert from mass of X to moles of X using the molar mass of silver nitrate. Then we need to convert moles of silver nitrate to moles of the other thing, which in this case is silver chromate. So we'll do a mole-to-mole conversion using the balanced chemical equation. So we'll need to use the numbers that are in here. And then we want to convert moles of silver chromate into mass of silver chromate so that we can compare it to the actual yield. So for that, we'll use the molar mass of silver chromate. All right, so the first thing, according to our steps, is to convert mass of silver nitrate to moles of silver nitrate. And I know that mass of silver nitrate needs to go on the bottom so that it will cancel there. And we want moles of silver nitrate in the top. And so we need the molar mass. And we know that 1 mole is going to be equal to the molar mass. So 1 mole. And then we need to add up the mass to get the molar mass of silver nitrate. So it's going to be 107.87 for silver, and then nitrogen plus 14.01 plus 3 times oxygen. So we get 169.88 grams. All right, so there's the molar mass of silver nitrate. Now we need to have another conversion factor where we convert moles of silver nitrate to moles of silver chromate, because that's what we need to compare. So we're going to do a mole-to-mole conversion using the coefficients from the balanced chemical equation. So I know that moles of silver nitrate needs to go in the bottom here to cancel that. And then I want moles of silver chromate in the top. And the way I get these numbers is from the balanced chemical equation. So silver chromate is here, and there's nothing there, so that means it's a 1. And moles of silver nitrate is here, and there's a 2. So I put that there. All right, so far, we're at this point. We just converted to moles of silver chromate. So we need to go one more step to convert to mass of silver chromate using its molar mass. So we need to do one more conversion, and moles of silver chromate will go in the bottom, and it's going to be 1 mole because we're getting the molar mass. And then we need to get grams of silver chromate on top. So we need to add up those masses. So we get 2 times silver plus chromium here, 52, plus 4 times oxygen. And we get 331.74. I will say, as you do these calculations, if you don't get the right answer, most of the time it's because one of your molar masses was incorrect. So you always want to double check your formulas, make sure you type this in correctly. These numbers are usually where students get a little bit off, and that will mess up your final calculation. So now we have our setup all done. We need to type this in. So remember to multiply the top numbers, divide the bottom numbers. So we'll start with 0.500 grams divided by 169.88 divided by 2. I'm ignoring all the ones here. And then times 331.74 equals this number. We're allowed to have 3 sig figs to match the number that was given to us. So our answer is going to be 0.488 grams. Running out of space here. Grams of silver chromate. Ran out of space, but that's okay. And then that's the theoretical yield. So we just did this. It says to also calculate the percent yield. So to calculate the percent yield, if we refer back to our formula here, the percent yield is the actual yield from the experiment divided by the theoretical yield, which we calculated, times 100. So we'll take, to get the percent yield, we're going to take the actual yield, which is this number here, 0.455 grams. And we're going to divide it by our theoretical yield. This should always be bigger, because this is the maximum amount we could ever produce. This is 0.488. Our actual yield is just going to be a percentage of that, and that's what we're calculating, times 100. So 0.455 divided by 0.488 times 100. We're allowed to use 3 sig figs because this was division and multiplication. So we get 93.2%, which makes sense. That's actually a really good percent yield. It means when you did this experiment, your yield was 93.2% of the theoretical yield of what was possible if everything went perfectly. So that's a really good yield. It's not always going to be that high. All right, so that's how you do percent yield problems. You have 2 more to do on this worksheet. Good luck.